Evening, ladies and gents. Back by popular demand this time around. It's P7, Fleming's left-hand rule, episode of Dwight Doodles. Here we go. Right, let's put it into context first. So, all the rage, Elon Musk, everyone's buying electric cars. Now, electric cars, the wheel needs to spin, the wheel needs to rotate. In order to cause the wheel to rotate, it uses an electric motor. It's Fleming's left-hand rule that tells us how and why we can create an electric motor and cause the wheels to spin. Other popular other examples of the Fleming's left-hand rule are fans. So it's very, very hot in the summer. And what we want to do, it looks more like a flower, but there's our fan, and the fan rotates. What causes that? Well, it's an electric motor. And how do we know what happens in an electric motor? It's Fleming's left-hand rule. Drills. Again, drills work on rotation. That's my poor attempt at drawing a drill. The drill rotates and the drill bit rotates, and in goes your nail, and you put up your lovely chest of drawers. Now, let's dive straight into the higher level business. How does Fleming's left-hand rule and an electric motor work? So what I'm going to draw first off, very badly, is two permanent magnets. Okay, this is my north and this is my south. Now, what happens when you have two permanent magnets is it creates a magnetic field. This goes from north to south. Now, these, as you're fully aware, we can't see any magnetic field, but we know it's there because they interact with magnetic metals. So what we want to do, remember, is we want to create rotation. We want to create spin. And with so, we have an electric motor that will drive our electric car. So the next part of the puzzle is we're going to introduce a wire. Now, if I have a wire like so, and I pass current through the wire itself receives a magnetic field from north to south around the wire. And that is the key to the electric motor. Let's go back to our wonderful permanent magnets. What we'll do, once I've gone through the concept, we'll then look at some questions for it. The next thing I'm going to introduce is our wire in this particular shape. And so what we're going to do is we're going to send the current along this rectangular shape of wire. This is going to be a DC current, and the current, obviously with a direct current, only travels in one direction. Get a bit more visual aid on there. Now, we turn on our DC motor, we turn on the current, we connect the circuit, and what we now have is current flowing through our rectangular wire. Now, if we then slide this into our permanent magnet's magnetic field, something very magical occurs. And this is where, ladies and gents, we introduce Fleming's left-hand rule. Now, I don't recommend you do this at home. Here's my left hand. This here is my first finger, and this is the force. That's the magnetic force from north to south. Now, obviously, you cannot do this in an exam either, because this will be deemed as cheating. The second finger, this is the direction of the current. And my little thumb, let's give it a little smiley face, look. This thumb M is the motion of the wire. So what we now have to do is take our hand. This you can do in an exam. Obviously, you can't write on your hand. And then, excuse me, place it. What would happen to this if we placed it in here and we turned on our DC current? That means current flows in one direction. Well, let's try. There's our force line, north to south. There's north, there's south. That's the direction of the force. There's the current line flowing in that direction. And if I just move my ham in shot, there he is. Look, Mr. Motion is going upwards. So if you place that in there, this side would move the wire upwards. Let's call it side A. This is side B. So once again, take your hand, Fleming's left-hand rule. There's the force, but I need to rotate my hand. Okay, so let's just see it again. North to south. But look, the current is flowing in that direction. So now force is there. It's a bit wonky donk. But you can see the current is in that direction. The force, I can't bend my hand that hard, but the motion is pointing downwards on B. And what happens is, if this was the sheet, it creates, B is going down, A is going up, and what happens is DC current flows, flow of charge, the wire gets a magnetic field, and the magnetic field, following Fleming's left-hand rule, side A will move upwards, the motion would move up, side B would move down, and the two magnetic fields interact, creating the spin. But when it's at right angles, exactly like that, it is momentum that carries it back into the magnetic field lines, creating that perpetual spin. And then you've got yourself your little electric scooter whizzing down the Oundle Road with a driving license, hopefully. That's the principle of the Fleming's left-hand rule. Start the video, stop the video, and you can follow what happened. Let's have a look at a higher level question. All right, and then we're going to up the complexity of what we need to be asked. It reads, a student placed a permanent magnet on a top hand balance. He clamped a straight piece of wire so it was suspended in the magnetic field. You've got your DC current here. Only works with DC current. And it said, when a current passed through the wire from A to B, the reading on the balance increased. Explain why. Well, we know with explain, we've got ourselves a little bit of a state because. So what happened to the reading on the balance? Well, if we take our hand, our left hand rule again, we've got north to south. And when we pass the current, the first thing that's going to happen, the current, let's move this up, the current passing, flowing from A to B causes the wire to have a magnetic field. There we go. Okay, I'm going to give myself a tick and I'm going to correct my own answer. There we go. Secondly, when it gets a magnetic field, it will interact with the permanent magnetic field. So mark 2, the magnetic field of the wire interacts with the permanent magnetic field. Now, is the wire going to go up or is the wire going to go down? So we're looking for the motion. So let's have a look. There's our force. There is our current flowing that way. Let's just bring in our little friend. There's the motion. That's pointing upwards. So mark number 3 would be our friend Fleming. Fleming's left-hand rule says the force on the wire is upwards. Okay, is upwards. There's 2, and there is 3. And therefore, the force on the permanent magnet is downwards. Okay, that's the first question I want us to look at. Now, that's a high level question. If we now look at a more challenging high level question, this is in your homework pack, so you can actually use this when you're doing it, which is the whole point of these things. Right, got a beautiful electric motor here. We've got a north, we've got a south. There's our permanent magnet. We've got the split ring commutator here, which allows the brushes to just spin round constantly so no wires get tangled. It says explain why the coil rotates when there is a current in the coil. So once again, we already have our permanent magnetic field. When we turn on the circuit, then the coil will have a magnetic field. And so the answer will be current flows in coil. It's going to be pretty much the same as before, and that's the key to passing. Familiarity of questions. If we look at the picture there, then we look at the picture there, they are slightly different, but the process is the same. Current flows in the coil, there's the coil. By doing so, current flows in the coil and creates a magnetic field. This interacts with the permanent magnetic field. Okay. Current, remember, in the coil, and this is why it's a challenging question, because if it looks like that, and therefore the current is in opposite directions on each part of the coil. Current flows in opposite directions in the coil. All right, so we've got one there, we've got one there. So then the forces, remember, so there is our north to south. But then if we actually north to south, but turn it that way, okay, the motion on side A would be down, but then we've got the north to south and the current flowing this way. If you look, north to south, current, abosh, and the motion is up. So the motion is up. So you've got down and up. So the forces acting in opposite directions on each side of coil. And then the final mark is, I believe, when they spin round, and if we just focus in on the split ring commutator, you've got this brush that runs around this here. And this, excuse me, ensures that the current is in the same direction. All right, the current is in the same direction. Now your homework is this booklet, but you do need to go through that again based on Fleming's left-hand rule and the electric motor. And I did that with 10 seconds to go. There you go, perfect timing.